Hello, welcome to Econometrics Melody. In this video, we will discuss about the properties of the mean, some of the properties of the mean. So let me write it as properties of mean. And in matrix notation, we know that I is equals to, let me take only 3 observations, and then any hypothetical variable that is a vector x with 3 observations. Let me take it 1, 2, 3 for our convenience. This is a very simple example, and 2 is the mean. So our first property is that the deviation from mean, and if we sum, so sum of the deviation from mean is equals to 0, and we want to prove it. So first of all, let us say the deviation, let us take a vector x, and its mean is 2. It is quite obvious. And let us see whether it's deviation from mean. Let me call it a d, and this is equals to x minus x bar. So let me call it as I x bar, and this is equals to the value of x is 1, 2, 3, and the minus, and its mean I into, let me substitute the value of mean over here, and this is 1, 2, 3 minus, and here 2, 2, 2. So this is the deviation from mean: 1 minus 2, 2 minus 2, and then 3 minus 2. And if we further solve it, this is minus 1, 0, and then 1. And if we add this 2, so this is the deviation. So we are talking about the sum of the deviation. So if we sum it in terms of matrix I transpose D, this is equals to 1, 1, 1, and then the deviation is minus 1, 0, 1. And this is equals to, if we simply operate and use the dot product or simple multiplication, this is equals to minus 1, and then plus 1 into 0 is 0, and then plus 1 into 1 is 1. So minus 1 and plus 1 is cancelled out, it is 0. Now we are going to prove this theoretically. So for the general notation, let us see, we know the mean or deviation from mean is equals to x. So the elements or every observation in x minus x bar, and we're going to use the summation. This is what we mean by the sum of the deviation. This is equals to summation of x minus x bar, and let us operate it. This is summation x minus summation of x bar. This is equals to summation of x, and x bar, this is constant, and if we add this so many number of times, so if we add this constant so many number of times, then we get it is n into that value. So for this particular case, this is the mean. So if we add this, this is equals to 3 into 2, so the sample size into 2. So this is the case. Now let us say summation of x, and the average value is, we know we have the average value or the average of mean, and if we multiply it with the sample, this is also equal to summation of x, because our x bar is equals to summation of x divided by n. Therefore nx bar is equals to summation of x. It's very simple, and we can cancel it out. Therefore this is equals to 0, and hence we have proved that the sum of the deviation from mean, this is equals to 0. This is our general notation. Now let us prove it by the help of matrix notation, and we have already seen it by the help of examples towards our right. Now let us say, we have already seen in our previous video that the deviation from mean matrix is given by I minus I transpose divided by I transpose I, where I transpose I is simply the I transpose I is, and this is our sample size. Now let us consider it for the case of the vector. So we have the deviation d is equals to the vector x minus, we write it as I x bar, and then I x bar. If we compare it with this, then after, let us take the sum. So in matrix notation, taking sum means we use this I transpose d. This is equals to I transpose and x minus I x bar. So this is equivalent to the summation of the deviation. Now let us operate it. I transpose x minus I transpose I x bar, and here we have I transpose x minus I transpose I is equals to m. Otherwise, let us leave it the way it is, and let us write it as x bar. X bar is equals to I transpose x divided by I transpose I, and this cancels out. They are the same. N I transpose I is equals to n, the sample size, and this cancels out. So we are left with I transpose x minus I transpose x, and this is equals to 0. Therefore I transpose this means the summation of the sum of the deviation from mean, this is equals to 0. Alternatively, we can use this as well. So our matrix, this is our deviation from mean matrix, and this is equals to I minus I transpose divided by I transpose I. And to calculate its a sum, let us use I transpose m0. So this is the sum of the deviation, and this should be equal to I transpose and then I minus I transpose I, and let us see what happens. This is I transpose I is equals to I transpose minus this is I trans. When we operate it, first of all we write this, after we write this entire thing. So it is I transpose, and then I transpose I. And if you look at this, we see that it is I transpose minus, and then this is I transpose I. This part and this part, they are in. We can cancel them out, and we are left with I transpose, and this is equals to 0. Therefore, I transpose M0 is equals to 0. And alternatively, we can write it as M0 transpose I, and its entire transpose is equals to 0, because we know that A into B transpose is equals to B transpose into A transpose, and this is an idempotent matrix. So as it is an idempotent matrix, this transpose is equals to the matrix itself, and when we multiply it with itself, the result is again itself. So this is our result. Therefore, we know that we can say that M, and further here M0 transpose, this is equals to M0 itself. So M0 I, or we can say it I dash M0, this is equals to 0. So we have seen that the sum of the deviation from mean, this is equals to 0. This is one of the important property of the mean. So I will state it in terms of equation. Let us say that a variable x, its mean is x bar, and its variance, it is represented by s square. So we have constructed a variable y that in such a way that we took this variable x and we scaled it by this factor after we shifted its origin by this unit. And let us see what happens to their mean. How do we establish the relationship between their mean? So to calculate the mean, now let us use summation y on both the sides. Summation, let us use summation, or let us take the sum on the both sides. So this is ax plus b, and let us operate it summation ax plus summation b. And if as a is constant, we can take it outside and we can take the sum of x plus, if we add the constant n number of times, then we get it is n into b, because this is a constant and we have n number of observations. So this is equals to n times b. It is very simple. This is what we mean by summation of y. And then let us divide both the side by m to calculate their average. Summation y divided by m, this is equals to a summation x divided by m plus b divided by m. So this is equals to y bar and the a x bar plus, let us cancel this out, and it is b. So what did we get? Actually, we had constructed a variable y is equals to ax plus b. We scaled the variable a by this unit, and then we shifted its origin by this unit. So the average of that variable is equals to this relationship. So the average of y is also equal to the average of x scaled by the same unit and translated, or the origin shifted by the same unit. So this is a very important property. Let us see its matrix counterpart. So we have let us now call it as a vector. So this is the vector x, and we're going to construct a vector y. First of all, we multiply this vector x by some unit a, and then we shift its origin by b. So in matrix notation, we write it as I, because this is constant. Now let us take its sum. To take the sum, we use this I transpose on both the sides. I transpose, then after it is ax plus ib, and then this is equals to, and let us operate it I transpose ax plus I transpose ib. This is equals to I transpose y, and then a is constant, so we can take it outside. I transpose x plus I transpose ib. And to calculate its mean, so let us divide by n. That is equivalent to dividing by I transpose I on the both the sides. So if we divide by I transpose I, that is equivalent to multiplying it by I transpose I inverse on both the sides, I transpose y, and this is equals to a is constant over here, and I transpose I inverse I transpose x plus I transpose I inverse I transpose I and beta. So this is the average. This is y bar is equals to, and this is again x bar, a into x bar plus, and they cancel out, and we're left with b. So we had started off with y equals to ax plus ib, and we ended up with this relationship. The average of y is also scaled by the factor a plus b. So the average of y also maintains this relationship where the average of x is scaled by a and the origin is shifted by b. So this is an important property, and we have seen it using the general notation as well as using vector notation. And this is true for the matrix as well. So this is it for this tutorial. Thank you very much for your time. Thank you very much, econometrics Melody.